Hello and welcome to 8A. This will be on tides. I'm a little worried about this chapter because I don't know how much physics to get into. Um, Basically what we do is we have an attraction between objects. It's called gravity, and you can see the gravitational attraction is G. We have a centripetal force because this planet is actually spinning, and you can see that as the red C. And then we have the resultant, which way the water is moving, and that's this blue line, which should actually have an R, but it doesn't. But you can see we have the largest gravitational force going this way, the smallest gravitational force going this way. We have a centripetal force, we have a centripetal force, and we have the resultant. So going away from, on this alignment between the moon and the earth, going away from and going toward, and this has to do with the gravitational difference between this area being closest being pulled more, this area in the middle being pulled not quite as much, and this area being pulled not much at all. So what we do is we get two bulges of water. This diagram is actually showing you that the water on this planet is being pulled towards this line, and this one's being pulled toward this line, and it actually is more of a squeeze. And this is the part of the physics I don't want to get into. It's more of a squeezing of the water along this alignment of gravity. Well, I'll try to see about what I can do with this later. What are ocean tides? Ocean tides are the cycle of rising and falling water and sea level. They tend to be one of the most reliable and predictable phenomenon that we come across. In fact, you can probably find tide tables for the year 2116 if you look far enough. And we can actually now find charts showing the high tide and low tide for most locations on the planet. These are the high tides with the greatest variance. This is the low tide with the smallest variance. And then we have the tidal swings with the greatest value. And you can take a look at probably the largest number there is probably close to the smallest there and probably close to the largest variance there, all happening on Thursday. This was actually in 2009, but March 12, 2009. And that when it happened right around 3 o'clock in the morning. What are ocean tides? Tides are actually big waves. They tend to be about 12,000 miles apart. The crests tend to actually work for the high tide, and the trough works for the low tide. And you can see this one they're showing you it's about a meter higher. So this is a foot. So we have about 2 feet of difference between high and low tide at this location. Can we tell where this? This is actually in showing you 3 locations, one in Alabama, one in Florida, one in Mississippi, and you can see that they're not all created equal, although they do look very, very similar. When the crest or the highest part of the wave is there, we have high tide, and when the trough or the lowest part of the wave is there, we have low tide. So we have a difference, and if you take a look at it, we have them just about 24 hours apart, and we'll actually find out. So this is 12 noon, like 2 o'clock, and then 2 o'clock, and you can see it's actually a little bit farther away than 24, and it actually works out to be 24 hours and 50 minutes later each day. So as these things move, they move a little bit farther. And then we have what are called spring tides, and then we have what are called neap tides. Spring tide's the largest. Actually, I'll talk about that later on. What's the real question about how they work? So here are tides for Quantico, Virginia. This is Virginia station 863468.9. Not important, but it is Quantico, Virginia, close to us. And you can see we have high tide and we have low tide. It's a big wave, crests and troughs. And I picked this date because it's June 10th, June 10th, and June 10th. And where are some of you going to be on June 10th? I think that's the day of graduation. Tide producing forces. Okay, we actually have the sun. We have the earth moving around in a counterclockwise direction. We have the moon going around the earth in a counterclockwise direction, sort of going around this way. So there it goes, and then it comes back down, and then it goes back over and comes back down. And if you click these links, which I know are tough to see, but I will link them on this video, you can find how this is more of a vortex because the Earth is actually moving around, and if the planet, actually planets stay around going around the sun, going around this direction, the sun's moving at 70,000 miles an hour. We're actually moving through space as we move around the sun. Gravity and motions among the Earth and sun and the moon, this is what produces the tidal forces. If you take a look at what's called centripetal, Centripetal is actually where the moon is tethered. It's like tetherball. The center mass of the Earth is located there, but the center mass of the Earth-Moon is located there, and that's called the barycenter. And it's directed away from the barycenter. So if you take a look at the Earth and the Moon, then this is looking from the South Pole because it's got the Moon going around the clockwise direction. It really should be going around the other direction. But as this moon goes around, the Earth also goes around this barycenter. That's the center of mass. And you can see as the Earth moves away, that's where the moon is located. And as it moves toward, that's where the moon is not located. Here's another version of it, and you can see it's sort of like a teeter-totter. So they're moving back and forth. Barycenter in one direction, and if you look at the point of rotation is not in the center of the Earth. If you have really massively moving objects like massive here and massive there, the barycenter can actually be outside of the object as well. And you do have to remember it's 24,000 miles apart. So they're not as close as this, they're not as close as that, they're not as close as almost any depiction in terms of tides. They're very, very, very far apart. Resultant tidal forces. We have gravitational force between the Earth and the Moon. We have centripetal force between the Earth and the Moon, and we have what's called the resultant, which is where the water goes. And the water actually goes towards the center line on one side, bulges out, and that's the high tide. It goes toward the center line on the other side, and the center line between the Earth, the Sun, and the Moon. So we actually get a tidal bulge on the opposite side as well. Tidal bulges, water bulges away from the moon on this side, it moves toward the moon on this side. Sometimes it's the highest high tide, sometimes it's the lowest low tide, and then mean sea level is this. So if the water actually was the same all the way around the planet, it would be this direction, not pulled away, not actually pulled toward. And it's not actually being pulled towards the Earth, it's being pulled again towards that center line. And for this point, that would be straight down. And this point, it's almost straight down. So the Earth rotates beneath this tidal bulge. So when we actually rotate into this direction, we go to high tide. And then we rotate over there, we get a low tide. Then we rotate on this side, we get a high tide. And this actually tends to slow down the rotation of the Earth because we're actually moving into these bulges all the time. And if you actually went back to dinosaur time 65 million years ago, you'd find out the Earth's days were probably about 22 hours. Now they're 24 hours. So we wait another 65 million years, we may actually be 26-hour days. That's going to affect the time, how many days we actually have in our year. So hang around for 65 million years, we may have a different calendar. So what this does, it gives us 2 high tides, 2 low tides each day. Complications with the simplest form of equilibrium theory, in other words, that 2 and 2. Oceans don't cover the entire Earth. We have 29% land. Oceans do not have uniform depth. We have the deepest ocean, and we have a shallower ocean on this side. Friction between the ocean and the sea floor, as the Earth actually rotates in this direction, the water drags against the sea floor, which slows the motion of the bottom, which slows the motion of the next layer, sort of like the Ekman transport. It keeps getting slower as we, or less slow as we move up, but it continues to slow down. Continental interference, as the bulge actually moves into the continents, or the continent moves into the bulge, that can have an effect on the bulge itself. And moon's not always in the same place in respect to the Earth. It actually moves around the Earth every 29 1/3 days. Lunar day is longer than the solar day. Takes the moon, like I said, almost a month to go around. That's where the name month comes from. Takes solar day only 23 hours and 56 minutes. And here's the lunar day. Lunar day is when the moon actually moves all the way around, and you can't see it moving all around here, but basically it goes around the entire planet, and that would take 27 1/3 days. So the moon moves, and if you watch this man, 8 hours later, the man's going to be located right there, moves from high tide, moves through the low tide, moves into another high tide. And then 8 hours later, it moved through that tide and over to this location. And then 24 hours later, it's located right here, same place it was, straight up and down. But what happened is the moon is actually revolving around the Earth. So 8 hours later, the moon has moved from this dotted line over, and then it's moved a little bit more, and then it's moved more, and it actually takes an additional about 50 minutes for the man to catch up to the moon line. This is a solar day, and that's a lunar day. In fact, moon revolves around the Earth. Earth has to catch up to the moon to reach the same position, and the true 360-degree rotation. This point right there is not really 24 hours, because what's happening is the Earth moves around the sun, which moves the sun a little bit, like 1 extra degree. And it really, if you were doing a Trivial Pursuit game and you talk about how long does it take the Earth to rotate 360 degrees around its axis, the point is 23 hours and 56 minutes and 4.1 seconds. So it takes an additional almost 4 minutes, 3 minutes and 55.9 seconds for the Earth to actually catch up to the moving sun. And then the last thing we have to talk about is that 50-minute. If you take a look, we've got high tide and we've got low tide, and we've got high tide and low tide. But if you look at the difference between 6:32 a.m. on one day, February 18th, and then you go to 6:56, if you look at that, we actually have, it looks like 24 minutes, and then you do another one of those, and you get to about a 50-minute time each day. So time between successive high tides shifts day after day. Moon rises later each successive night, about 50 minutes later each day. And it's also shown with this diagram. And I'll wait until it starts so you can see the moon's moving there. And it takes an additional time for the Earth to catch up to that moon. But if you start right there, and then we go a quarter of the way, 12.5 hours, halfway, 25 extra minutes. There we have an extra 12.5 minutes, and then there we have the additional 12.5 minutes to make it 12.5, 25 minutes, 37.5 minutes, and then a 50 minutes to catch up to this revolving moon. And then you can see the high tide, low tide. So as it moves around, high tide opposite side, low tide 90 degrees to that, high tide when it catches back up to the moon, and then low tide, another high tide, and this will be the last one, I promise. And there's the low tide, and there's the high tide. And then that bear signifies that's the end of 8A tides. Thank you.